In this series of videos, we will cover the course material of Mathematical Analysis 1, or Real Analysis 1, going over all the concepts that one can expect to encounter when taking this course at a university as part of a mathematics or physics program. Mathematics is basically a series of statements that we categorize as true or false. You may be thinking to yourself, well, so is life as a whole, what's your point? But the distinction is that in mathematics there is no in-between. It is a binary situation. Either the statement is true or it is false with no room for debate. This decisive nature of mathematics makes it an exceptionally powerful tool for understanding the world around us. But it also comes with a significant burden, as we must be very precise. I'm talking cutting the blue or red wire levels of precision here. So let us go through the fundamentals of logic in detail to make sure that you choose correctly. Logical operators and statements provide us with the framework to express mathematical statements. There are 5 operators that we will regularly encounter. First off, we have the negation operator. This operator can be applied to a statement to invert its truth value. If the initial statement is true, then the negation is false, and vice versa. The negation operator rarely appears on its own. Its true value is only really visible when combined with another operator. Secondly, we have the AND operator. This operator only makes sense when connecting 2 statements to each other. The resulting AND statement will output true only when both statements are true, and will give false otherwise. A common use case for the AND operator in mathematical statements is in constructing the setup. You will frequently see statements that start with something along the lines of let n be real and positive, or let S be a non-empty set and let M be a subset of S. The AND in between indicates that the upcoming result is dependent on both assumptions being true. In some cases, you will need to verify the validity of your assumptions, as we will discuss later. Thirdly, we have the OR operator. Similar to the AND operator, it links 2 statements to one another, but it outputs true if the statement holds, and only outputs false when both statements are false. Unlike the AND operator, we encounter the OR statement much more frequently in the final part of a mathematical statement, rather than while establishing the starting assumptions. A common example comes from algebra in the form of if x squared is equal to 4, then x equals 2 or minus 2. One of those solutions will always be true, so the use of the OR operator is allowed, as one can see from the truth table. The if or implies operator also connects 2 statements, and it outputs false only if the first statement is correct and the second is false. We have already seen the if statement in the previous examples, and it serves to detail the logical flow of the statement. Notice, however, that if the initial statement is false, then any conclusion can be drawn from it, and it can be true, thus making the statement meaningless. For example, the statement, if unicorns exist, then they will cause a recession in Australia, is meaningless. The idea here is that since unicorns do not exist, it is impossible to determine whether they would or would not cause a recession in Australia if they happen to exist. Lastly, we have the if and only if operator, or the if operator, which outputs true when the 2 statements have the same truth values. If 2 statements can be connected by an if and only if operator, then they are essentially equivalent to one another. Essentially, an if and only if operator is a combination of 2 statements. If A then B, and if B then A, meaning that each should be checked separately when constructing a proof, since it is not sufficient for either to be individually true. One way to verify that 2 statements are indeed equivalent is through looking at the truth values. Let us look at an example to see this more clearly. Not A and B is equivalent to not A or not B. Since this is an if and only if type statement, we should verify it by writing down the full truth table for both statements and then confirm that they have the same values, which you can see on the screen now. When given an implication statement, we can extract 3 different statements from it, known as the converse, inverse, and contrapositive, as expressed here. If the statement is if A then B, its converse is if B then A, its inverse is if not A then not B, and its contrapositive is if not B, then not A. It is important to realize that a statement being true does not imply that its converse or inverse are true, but it does imply that its contrapositive is true. To see this more clearly, pause the video. Try writing out the truth table for yourself, and then unpause to check if you got the correct result. If both the statement and its converse are true, then we have an if and only if type statement, and therefore the inverse and contrapositive are also true. We close this video out by introducing 3 symbols that you will frequently encounter in mathematical proofs. There exists. This symbol states that at least one element exists fulfilling some statement. There exists exactly one, which states that that element is unique. And lastly, for all, which applies to all elements in a given set of some sort. Notice that negating a for all statement is done through a there exists type statement, and vice versa, since the presence of a single counterexample is enough to show that a statement does not hold for all, while negating a there exists statement needs us to show that the statement is false for all elements, therefore showing that no element exists that fulfills the statement. In the next video, we will take a look at the construction of sets and functions, which are a natural extension of the concepts discussed in this video.